Good morning, everyone, and I'd like to welcome to this edition of the Teagasc Research Insights Seminar. My name is Kevin Hanrahan, and I'm the head of Teagasc's Rural Economy and Development Programme. I'd like to wish you all a happy new year, and to get the new year started off like we hope it will continue. Today we're going to be talking about Teagasc research on technologies and methodologies that allow us to see what's going on with respect to our use of agricultural land in Ireland. This is part of a series of seminars run by ourselves in Rural Economy and colleagues in the Crops, Environment and Land Use Programme that has looked at land use, and we've seen presentations on economics, on environmental science, looking at things like biodiversity, greenhouse gas emissions, pressures on water and so on. This seminar is going to be a little bit different in the sense that we're going to be looking at some really interesting and innovative technologies and uses of those technologies that allow us to, in a sense, remotely observe what we collectively are doing with our land at various different geographical scales. And there's going to be 3 presentations today from my colleagues from the Spatial Analysis Unit, and they are going to take us through some of the detail of these technologies and methods and how they are applied in the case of land use and understanding changes in our use of agricultural land. And the discussion afterwards, after the presentations are finished, will hopefully tell us about where we're going to go next with these technologies, how they might be applied in other fields, and I'm sure that you'll get a lot out of it. So the first speaker is going to be my colleague, Stuart Green. Stuart is Research Officer in the Spatial Analysis Unit, and Stuart's going to be looking at how satellites and data from satellites and information generated with that data that data can tell us about the productivity and the footprint of Irish agriculture at various different geographical scales. I'll introduce the other speakers as their presentations start. But for now, I'm going to pass you over to my esteemed colleague, Stuart, who will take us from here. Thank you.
Thanks, Kevin. So we're talking about technology that we use to look at land cover, and we're using satellites. And so we wonder, well, to begin with, what can satellites see? Well, sometimes satellites can see everything when we're lucky, but most of the time in Ireland, we see only clouds. If we want, we can make a satellite image see an entire hemisphere, half the world, and you're familiar with these from weather forecasts. But new technology allows us to zoom in with such detail that we can see cattle grazing in fields. So we get holistic views, we get close-up views, and it's useful because Teagasc has been in the business of land use mapping for a long time, even before Teagasc existed in the old days of AFT. And this was boots on the ground mapping for soils, for land suitability, soil suitability, and land use. This new technology of the satellites does allow us to speed things up and see in detail what you can't always see on the ground, because the satellites allow you to see everything. And there are about 900 of these Earth observing satellites in orbit now, at a total of about 2,500 vehicles in orbit. But we use a tiny fraction of them from the European Space Agency Copernicus program and from NASA. And for the purpose of this morning, you can think of these Earth observation satellites as just digital cameras in space. So they're orbiting anywhere between 250 and 500 kilometers up, and they orbit around the world roughly once every 75 minutes. And some only go back to the same place every 16 days. But some of the newer systems that have just been launched in the last year or two mean that we can view any point in the Earth multiple times in a day at quite high resolutions. And if you think of them just as giant digital cameras in space, and they're taking photographs in much in the same way as the phone or the camera on your phone. And it's the same thing, we're measuring reflected sunlight, and the sunbeams, the photons from the sun shine down onto the Earth. and they have to pass through the atmosphere. And when they're passing through the atmosphere, we get things like scattering, absorption, transmission, reflection. This is why the sky is blue and we get red sunlight, sunsets and sunrises. And when it gets to the surface of the Earth, all these processes happen again. The sunlight is absorbed, some of it is reflected, some of it is scattered, and then all the way back up through the atmosphere. So these are really complicated processes that we have to concern ourselves with in terms of the physics. But for now, all you have to think about really is that grass is green. And it's green because it absorbs red light and it absorbs blue light as part of photosynthesis, but it predominantly reflects the green light. So it's the green light that our eyes see, and this is why grass looks green to us. And it's this color, this fundamental color, that allows us to do nearly all the work we do with these satellites. So this is what we call a true color satellite image. This is somewhere in the Midlands. And if you were strapped to the satellite in the moments before you suffocated in the vacuum of space, this is what you'd see. This is what the world looks like from space. And we live in the electromagnetic spectrum. We live in the visible part of the spectrum. So we can see blue light, yellow light, orange light, up to red light. But the satellites have a trick. They can see parts of the spectrum that we can't, and this really makes them very useful. So instead of just recording everyday imagery, the satellites can capture energy and data in different parts of the spectrum. And this is what we call a false color image. So this is an image where the satellite has captured information in what we call the near infrared. This is wavelengths of light that are just a bit longer than the red light that we can normally see. And the interesting thing about this is that plants strongly reflect the near infrared. So these subtle shades of pinks and reds, they tell us an awful lot about the vegetation that's growing, about how much vegetation is there. It tells us about the type of vegetation, the age. It tells us a great deal of information, and it's manipulating these colors and understanding these colors that will allow us to do the work myself and my colleagues will be talking about today. Just a quick aside on this issue of resolution. People sometimes wonder about how good the satellite images are and how much you can see. This is the same area viewed at two different resolutions. This is a coarse resolution of 250 meters. This is 1 meter resolution. And whilst, okay, this is very coarse, I think you can see these dark green blobs represent the dark green forestry. So there is information we can capture at even these coarse levels. And what resolution is, if someone says that the image has a 10-meter resolution, what it means is that objects on the ground have to be separated by 10 meters or more for them to be resolvable into two separate objects. And there's a whole range of scales. So we have the NASA satellite MODIS has got a resolution of 250 meters. So this sees broad areas in little detail. We have Landsat at 30 meters. We have Sentinel at 25 meters and 10 meters. We have Spot at 1.5 meter resolution. Just zoom in there, that's a sort of detail that Spot, the French satellite, can give us. And then the commercial high resolution satellites are sub-meter. They're down to like 40, even 30 centimeters in some cases. So that gives a lot of information. But generally speaking, the higher the resolution, the smaller the image, just in terms of memory size and the ability of the system to capture data. And what we can do once we understand color and how light is reflected off different surfaces, we can do what's known as classification, where we can take land cover, we can take an image like this one, manipulate it, train it to create a map like this, where we've recolored all the pixels to represent different land covers in the landscape. And just to say that land cover, land use, habitats, land management, they're all different things and they interrelate with each other. I think the easiest way to think about it is that land cover is what if you're in a field, land cover is what you're standing on, whereas land use is the reason you're in the field. So the land cover might be grass, but the land use might be grazing. Or the land cover might be grass, but the land use might be silage cutting. So you can have multiple uses from a single land cover. And using what we call sort of classical methods that just look at how similar colors are in each pixel and band them together into groups that are similar, using supervised classification, we can do a lot of good work. So we created the first national land cover and habitat map for the country using this technique from satellites. And these in turn fed into the first digital soil map. So we had a digital model of soils based on what we know about the geology and the land cover. We can predict the soils. So we have a digital land cover map, a digital habitat map, a digital soils map. And we tried to bring all these things together in a recent project with colleagues in Trinity College called SOLAM, where we looked at the relationship between the different soils in the country and the different land cover and land use classes. So we were able to break up the soils into 4 main groups, and we can then relate those groups with the different land covers and habitats. So we have 4 soils: purple, green, red, and blue, and these are the breakup against the different land uses. So this gives us a good understanding now of these relationships, and it allows us to do things like carbon modeling for the country. And once we have a soil map, once we have a way of looking at land use, and once we have a way of looking at productivity, as my colleague Risha will talk about in a few minutes, we can start to do things like map all the grasslands that are over organic soils. And this is an important topic for a lot of reasons, for habitat mapping, for productivity reasons, and more importantly, in the last few years, in terms, again, of carbon and carbon storage, and increasing carbon storage in Irish soils. So we now have this map of grazed or managed grasslands over peats, all from satellite. In the TALAM and ILMO projects that we did with colleagues in FIRS and UCC and funded by the EPA, we refined these methods of classifying land cover so that we could understand better the particularities of doing this project in Ireland. And we discovered that April is the best time to map land cover and land use. The different categories are more separable in April than any other time of the year. But we also discovered that it's important that we have a lot of information that goes into our models, and we use multiple years. So we need multiple years of data, and we need multiple sources of data. And that way we can get accuracies up to 90, even 95% accurate. So we created the Earth Observation Archives. This is every satellite image that's been captured for Ireland from Landsat and Sentinel, going back to the mid-80s up till today. Excuse me. And this allows us to get the history of every parcel of land in the country. And we can go back and we can see what changes occurred. Has it gone from grassland to forestry, or from grassland to cropland, or from cropland to built land? We can see how frequently it's been covered. So this is a good way of looking for, say, permanent grasslands, areas of the country that have never been ploughed, or at least not in that satellite record. So having this archive is really important for land use modeling and for understanding how land use changes. And it means that we can go back from today. So here's an image from yesterday of the south coast, Cork's over here, or we can go back to the 80s. Here's a picture of the Burren in the 80s. So we've got a complete, deep archive and a wide archive of all the country and all the times. And this allows us to look at phenology. And phenology is the study of how plants change over a season. And we can look at essentially the greenness of the country or an individual field over time, going from January, February, March. We can look over between years, so we can see that this is the grassland curve. So we can see it changes. It goes up to a peak in the summer and down again in the winter. And then year on year, it changes. And having these long-term records of the phenology allows us to do a lot of work in terms of understanding average conditions and how things deviate from average conditions. And one of the things we can look at is spring growth, which is really important especially in the dairy industry for grasslands. And combining this with some of the other information that you've heard about in some of the other seminars in the land use series, we can get a really good model of how weather and growing conditions relates to farm practice and farm management. And so we can nowadays reliably predict when turnout will occur based on the current conditions we observed in the satellite, for instance. And we can see how turnout, this is when cattle are released from winter housing, changes as a result of the geography and the environmental conditions. So one interesting fact we published a couple of years ago is that for every 16 kilometers north from the south coast you go, turnout day on average gets 1 day later. Now, we try to use a lot more data than just we've discussed earlier. And one of the things in the ILMO and TALAM projects is that using radar data helps. Now, I said that in most of the times it's cloudy and we can't see through cloud, but there is one technology called radar, which can see through cloud. So that's Dublin on Sunday. It's taken at the same time with a different satellite called the Sentinel-1. This is a radar active satellite that can penetrate through cloud. So it's useful. And what we've found is whilst it does improve things a little bit, it's good at looking at change, but it's not very good at explaining change because it's essentially, it's a single channel. It's how strong the signal that went out comes back. So it doesn't have the finesse of the optical systems. But we've used it to look at grassland management. We can see when grazing occurs, when silage cutting occurs. It's very useful for looking at the removal of hedgerows, for instance. So we do incorporate it into our wider models. And lastly, I just thought it was a timely one, and I thought it was interesting. Last year with the wildfires in the spring, we were able to capture the wildfires happening in real time. So this is a satellite image of a wildfire in Wicklow in the spring, and we can see the burn edge, the leading edge here, and the smoke trailing away. But we can also, importantly, even if we don't capture it happen, we can see before and after pictures. So again, this is from the spring. So this is a before image, and this is an after image. And we can see the burn scar captured here. And this is useful for looking at the extent of burns and for putting them into models of carbon emission due to burning. So satellites, I've whizzed through that, but satellites can tell us a lot about Irish land use. Okay, so we now can use the satellites to tell us what agriculture is occurring, when it's occurring, and where it's occurring, down to the field scale. So we can see inside a field, as my colleague Rob will explain, and see exactly what's going on. And we can see the management history. It gives us detail and it gives us overview. And it gives us really useful statistics on land use and land use change. So we can understand better what's happening in the whole in Irish agriculture. Thanks for listening.
Thanks very much, Stuart. That was really interesting. I'd like to just remind everybody, and I should have done this at the start, that they should feel free to just use the Q&A function at the bottom of their Zoom screen if they have any questions about Stuart's presentation, about the presentations that will come, or about the topic in general. And at the end of the presentations, we'll have about 15 minutes to hopefully answer as many of those questions as possible. Next up is my colleague Risha Marwaha, who is a Walsh scholar working in UCC and with Stuart in the Spatial Analysis Unit in Red P. And what Risha is going to talk to us about is the use of remote sensing to get a deeper and better understanding of grass growth, which of course is at the heart of a lot of Irish agriculture. So Risha, I'm looking forward to hearing your presentation and seeing it, and over to you.
Thank you, Kevin. As Stuart discussed about remote sensing and satellite images, I'll be talking more about its applications in Irish context. There are many ways to monitor grasslands. Broadly, they can be classified into two parts. One is traditional in situ methods, and another one is remote sensing methods. In traditional methods, they are like eyeballing methods, cut and dry method, using rising plate meter in the field, and field spectrometry. The remote sensing methods include satellite images, for example, optical images and microwave images. And finally, the use of drones in the farms. Now, these approaches can be used to monitor the grasslands, its productivity level, and local growth rates. In this presentation, I'll be focusing on optical remote sensing. Now, this is an image from MODIS satellite data, and this is a time series for 2005 till 2011, and this represents phenology of grassland. But this is a coarse resolution satellite data, which means it cannot tell us a lot about within farm and paddock information, but it can tell us about local grass growing conditions. Hence, it can be very useful. In the next 2 slides, I'll be talking about its applications in grass monitoring. Now, this is one example of use of satellite data to compare the current grass growing conditions with average grass growing conditions. Now, we calculated 15 years worth of average of data, which gives us average grass growing conditions at one place. Now, when we have current conditions, we can see how we are deviating from that average. For example, we can be few days ahead and few days behind normal average growing conditions. Another example is looking at impact of weather on grass growth rate. Now, with this satellite data, we calculated a moisture index, which can gives information about dry areas in Ireland. Those dry areas can further lead to lower grass growth rate. Now, in this figure, when we see there are brown patches, which means that they are affected by the dry weather, which in turn can lead to lower grass growth rate. Now, there are a few methods to estimate grass biomass remotely at a national level. These methods are, first one is simple regression models. Next is biophysical models. These are crop models, which depends upon plant physiology. And third one are machine learning approaches. Now, I'll be talking about machine learning approaches in my next few slides. Now, before moving on to that, I'll explain what machine learning is. Now, machine learning is a subset of artificial intelligence, which has ability to learn from experiences, learn from the input data. And once it is trained, it can be used to make predictions. Now, this is a general pipeline of machine learning algorithm. First one is getting all the input data that you want. And using that data, we'll build a model. Using that model, we can make predictions, and those predictions can be further evaluated with respect to your reference data, and our output can be visualized. Now, the first attempt at machine learning in Irish context was made by a former PhD student, Iftikhar Ali, and he modeled grass biomass for 2 sites in Ireland, Moorpark and Grange. And he used machine learning algorithm and MODIS data for biomass modeling. The main thing here was now we want to expand this model to a national level, because at a national level, we need an operational decision-making tool which has more sites. Hence, we need more data sets and to explore new algorithms. Hence, in my PhD work, I explored new data set, which is Sentinel-2, which has better resolution than MODIS, and new algorithm, which is random forest. Now, it is a supervised learning algorithm, which is composed of many decision trees. The input data was satellite data, which was converted into NDVI, and meteorological data, which is, for example, rainfall, sunshine, soil moisture deficit, and temperature. This input data was fed into a random forest model, which was then used to make predictions. And the output of that model was evaluated using pasture-based Ireland, which is our reference data. It is a web-based decision tool in which a farmer can sign up and give information about his farm. It's developed by Teagasc. Now, I started with one site in Ireland, which is Moorpark. Then I used that approach expanded that approach for 8 farms, 8 Teagasc research farms. And then finally, I worked on a national model, which included 180 farms. So I'll be presenting the results for these 8 farms first, and then finally the results for national model. These are the results for those 8 farms here, Teagasc farms. The upper row represents training data results, and the lower one is for testing data. For training data, we got 0.93 R square, and for testing data, we got 0.69 R square. Now, these were only for 8 sites, and the results were encouraging. Hence, we decided to move on to include more and more sites to make a national model out of it. Now, while moving on to a national model, we followed a slightly different approach. First of all, we didn't have a lot of data sets for temperature, for solar radiation. Hence, we included only rainfall. And we had all the spectral bands and NDVI as input data. Now, the difference in approach is this. This is a general grass growth curve of grassland. And we decided to divide this curve into 2 parts. So hence we have 2 models. That first one is from January till June, and second one is from July till December. The reason to divide it into 2 parts is that during the first half, we have spring and we have more satellite images and the weather is better. So, and also the grass growth rate values are higher during this time. And from July till December, we have a few number of images and the weather is not that good, and hence the grass growth values are in lower range categories. So I had 4 years worth of input data. So I divided into 3 parts. First of all, I kept 2020 as evaluation data, which is completely independent, just to test how my model is working. And 3 years of data, which is 2017 and 2019, I shuffled them up and divided randomly into 70% of training data and 30% of testing data. And finally, that trained model was used to make predictions on 2020 data, which I'll be showing the results for. Now, these are the results for 2020 data for 180 farms. So on left-hand side is the model from January till June, and the right-hand side is from July till December. The earlier trained model, which was for 2017 and 2019, that model was used to make predictions for this 2020 data. Now, earlier result was for all 180 farms in Ireland. But for this, to get grass growth curve, I chose one representative farm in Ireland and plotted its grass growth curve just to see how it looks. So on left-hand side, I have January till June grass growth curve. The line with dots are actual data from pasture base, and the other one is estimated from random forest model. And on the right-hand side, we have grass growth curve from July till December. And again, the dotted lines are the actual data from pasture base, and the other one is from estimated data from random forest. Now, this model has can give us overall national view of how the farms are performing and also how each farm is performing locally. So the key messages are we can successfully map grass growth rate using machine learning and satellite data, which can give us overall national view of farms in Ireland. And now I'm currently working to test, to create the final map for 2020 data for Munster region in Ireland. And as more and more data sets will come up with high resolution, it can be used to train machine learning algorithms, which can help to improve the accuracy. Thank you.
Thank you very much, Risha. And welcome back to looking at our faces on the screen. Again, I'd like to remind everybody who's attending the seminar that they can use the Q&A function at the bottom in the middle of their Zoom screen to send in questions about Risha's really interesting presentation on the use of remote sensing and machine learning to understand grass growth at farm and field scales, or questions about Stuart's earlier presentation, or questions that might come into their minds as they listen to Rob O'Hara's presentation, which is coming next. Rob O'Hara is a former PhD student of Stuart's, I think, in the Spatial Analysis Unit, who's now a postdoctoral fellow with the Science Foundation Ireland Vista Milk Centre that's based in Moore Park. Rob is going to talk to us about using remote sensing and photography methods to map habitats on Irish farms using machine learning algorithms. So Rob, over to you.
Great, thank you, Kevin. Okay, so as Risha outlined in her last presentation there have been ongoing improvements to the resolution of satellite imagery that's had a very positive impact on grass monitoring here. And before that, Stuart noted how satellite mapping is frequently at the mercy of cloud cover in Ireland. Both these issues have been largely eliminated in the last few years with the emergence of mapping drones, which we can now deploy on demand and at specific locations on farms. So it's no longer a case that we have to make do with sparse satellite images. We can now collect huge volumes of data when and where we want it. With satellites and drones combined, we can look at farms in incredible detail now over a range of scales. Whether we want to look at the entire farm or its surroundings, focus in on specific fields or paddocks, even patches of grass, right down to individual plants if necessary. At the same time, there's been advances in computer hardware, software, some of the algorithms that Risha has outlined that are making it simpler and faster to process this data, analyze it, and then deliver the results to farmers. Depending on the type of thing that you want mapped on a farm, there are a range of options available. There's still plenty of free satellite data from NASA and the European Space Agency that can be used. As Stuart noted, there's some high-resolution satellite data providers. There are providers here in Ireland who will provide aerial photographs, multispectral aerial data as well, at a cost. You can purchase a drone, do your own mapping. Prices here start at a few €100, but go up to several €1,000 for more professional grade models that can carry lots of different sensors or specialist equipment. There are also a range of payloads that can be carried, multispectral, thermal, LiDAR, this sort of thing, all of which come at a cost. Then you need to get your processing software, depending again on what it is that you want to map. But as I'm going to show in the next couple of slides, even some of the cheaper off-the-shelf drones that you can get here still have very practical uses that can be put to work on farms. So from the next few slides, I'm just going to outline some of my own experience using drones and satellites for precision mapping here. And again, highlight some of the things that we have been using them for in Teagasc. A lot of these are taken from my doctoral research, which was the Drain Map project, a collaboration with Maynooth University, where I looked at how different types of earth observation data, different sensors and different techniques could be applied to mapping field drainage properties on Irish farms. I'm also going to look at some of the results of my current research, which is looking at how smartphones and satellites can be combined to improve land use mapping here. But this is only the tip of the iceberg. Teagasc researchers are doing quite a bit with drones. There are a number of other projects that are using high resolution data, for example, looking at improving greenhouse gas estimates, or looking at how we can map forest cover in better detail. But we're not going to have time to get into that today, unfortunately. One of the applications we looked at was finding buried drainage on farms. So drains are a major pathway for nutrient and pesticide loss, but often there aren't great information about where exactly drains are located on farms. Trying to find them, for maintenance or repair can be time consuming, but it's also helpful to know where existing drains are if you want to put new drains in. So using a drone equipped with a thermal camera in this case, we were able to detect buried drains over a wide area by observing small changes in surface temperature that was caused by subsurface anomalies surrounding drains. So taking a morning thermal image, and an afternoon thermal image, it was possible to distinguish some of the wetter soils and some of the drier soils by the rate at which they heated up. This study, in this case, was a sports pitch with well-organized drain lines. We still need to have a look in greater detail about how we can apply this information to agricultural grasslands. Another pathway for nutrient loss is in surface runoff. Knowing where runoff will generate on a farm and how it'll move within fields gives us a chance to target mitigation measures where they'll be most effective. In the past, we've used LiDAR to model runoff and identify hydrologically sensitive areas for nutrient loss at farm scale, but across whole catchments. LiDAR is particularly well suited to this because it gives very accurate measurements on the ground surface. But getting hold of very high resolution data can be expensive for an individual farmer. Photogrammetry, on the other hand, which uses overlapping images to build 3D models, is a cheaper method than LiDAR. The big difference between these two methods is that LiDAR can map ground level as well as canopy level accurately, whereas photogrammetry can only model canopy heights. So this would be a problem, say, if you were in a forested area where there might be several meters difference between the canopy surface and the ground surface, but it's less of an issue where canopy is lower or indeed bare soil. What we were able to show using drone photogrammetry is that the surface models we could create in that method were comparable to corresponding LiDAR models for intensively managed grasslands. So we were able to show that the models we predicted for nutrient loss were almost identical between the two methods, particularly at 5 meter resolution. Below this, in photogrammetry, the effect of grass height became a source of error. There are other concerns, I guess, with this method. Breakthroughs where flow transfers between fields may not be recognized if the boundary between the fields is an overgrown hedge, for instance. But nevertheless, it's a fairly quick and straightforward way to produce accurate 3D models within a field that can help farmers plan their mitigation strategies. Also, by using drones rather than just once-off LiDAR data, is that new maps can be created or updated over time as changes occur within a field. So, for instance, if a new roadway is built within a field, you'll want to know how that's going to affect runoff within that field. Photogrammetry, in the case of a road that's newly built, would be able to model and assess the camber on that road. So it would be able to observe over time how flow is changing on that road as it settles or sinks, see where runoff is going to come off that road, and whether or not it's going to pool and maybe cause damage by potholes. Drones aren't a prerequisite for precision mapping. When satellite data is available, as we've seen in the previous presentations, it can be sufficient to map certain processes. Here I used satellite NDVI imagery over several years to monitor improvement in grass growth following the installation of a drain on a heavy soil farm. In this case, we aggregated some of the satellite data for the entire field, an approach that we call object-based image analysis, to be able to just get some very straightforward statistics on growth in that field and monitor the effectiveness of the drains over subsequent years. As well as monitoring improvement, we can also monitor deterioration. So in this example, we used, again, a time series of NDVI images combined with radar flood maps to show how floods can have a prolonged impact on grassland production. The common perception with floods is that once the water recedes, everything is back to normal, the emergency is over. But with these maps, we were able to show that the lasting impact from floods in agricultural areas is poor growth that can last for several weeks or several months in some cases. And this is the kind of damage for which there's no emergency relief. Moving on to some of my more recent work, my current project, as Kevin said, is with Vista Milk, and it's in mapping land use and farm habitats. Grassland habitats exist as a function of management intensity, really. The more extensive management that's present, the higher the level of species you'll get. As management intensifies, these become species and habitat poor. Again, Stuart referenced how land use is the thing that's going on in the field as opposed to what you're actually standing on. It's a little more difficult to be able to classify land use because you need accurate, up-to-date ground truth data of what exactly is occurring there. These are the things you cannot often see in satellite images. In order to go out and collect that adds significant costs to any mapping project. But with smartphones, anyone can collect very high resolution data geotagged to a specific location and provide that as evidence for land use or show specific habitats. This is what happens every 3 years. Eurostat deploy surveyors across Europe to record and photograph land use at defined locations. So trawling through these thousands of smartphone photographs for hundreds of locations in Ireland, we can define different classes of land use intensity and then use these locations to train machine learning classifiers. Training machine learning algorithms on 3 years worth of optical and radar images, we were able to classify management intensity and detect paddock systems within larger fields with pretty good accuracy. The manual labeling of the photographs, however, is time consuming and often open to being subjective. Different people may see different land use in the same scene. So the issue becomes then, how do we remove this subjectivity? With some of my Vista Milk research partners from the UCD Insight Center for Data Analytics, we're working on a deep learning method using neural networks that will automate the labeling of ground level photographs in an unsupervised way. these can then be used for training and validating our satellite habitat and land use maps. This is going to radically change how we train and validate data and how we collect training and validation data for our maps. It's no longer a case of our boots having to go on the ground to gather this data. Evidence of land use can now be collected nationally by members of the public, by farmers, and submitted anonymously for automated labeling. This kind of technology, this kind of method has potential applications in streamlining the continuous assessment of farmland under new CAP reform proposals, where, for instance, farmers will be able to submit their own evidence to demonstrate regulatory compliance, which will reduce, hopefully, the requirement for farm inspections in the future. We see here just the difference in resolution, in what you can see between a smartphone versus a satellite image. In satellite images, management classes are very spectrally similar. So we need the information that's contained in the photograph to be able to properly train these machine learning algorithms to detect these different classes at high resolution. Okay, so that's it. So I suppose just to summarize, there are lots of different sources that we have now for mapping farmland. So we can do it with greater precision than before. This market is going to continue to expand over the coming years into all sectors of agricultural production as the technology improves. There will be also a developing role for Earth observation products in sustainable agricultural production and in, as I said, agricultural monitoring and evaluation. That's it. Thank you very much for listening.
Thank you, Rob. And can I ask everybody, all the presenters, to unmute themselves and turn their cameras back on, and we'll have about 13 minutes left or so for some Q&As from the audience. And there are questions in the inbox, so to say, and we would encourage you to keep on sending in your questions. So first, we have a question from a farmer in County Wicklow called Joe Hayden. And it's a question for Stuart, and he's asking about the use of these technologies and methods to measure carbon sequestration in farm hedgerows. So I think you know something about this, Stuart, so I'll let you spend some time answering Joe's question.
Thanks, Kevin. Yeah, Joe, in fact, we've done a lot of work on mapping hedgerows for carbon. In fact, I presented at a seminar just before Christmas as part of Hedgerow Week to show how it's done. So we've had, I think, 3 Teagasc projects on hedgerow mapping and carbon, and there's a 4th one being done by colleagues down in Johnstown Castle to improve the models. So it's perfectly possible at a farm scale to measure the extent and the size and the density of the hedgerow, and then model from that the carbon stored in that hedgerow and the carbon sequestered annually on there. We did it as an experiment on the farm in Douth, which was actually in a seminar a couple of weeks ago. So yeah, it's perfectly doable. I would just say that all our research shows that sequestration from hedgerow is at the low end of the range of emitted carbon that's in the Teagasc sustainability reports. So whilst it does improve net reporting at a farm scale, it's a long way from being a silver bullet. It's only a relatively small effect.
Yeah, so it's not a game changer, but I guess as we try to be as comprehensive as possible, it's great to have that knowledge, the data collected, and the processes that allow it to be turned into information we can use to better understand the world around us. There's lots of questions here for Risha, so I'm going to try aggregate a few of them before we come to ones from Rob. One question asked Risha from Matthew Clark asks about whether your models take natural variations in soil fertility into account in their grass growth predictions. Do you want to try answer that one for a start?
Yeah, no, I haven't taken account soil fertility in my models. Also for 8 farms, I have considered soil moisture deficit only, but as we move on to the national level, there's lack of data. So I'm not sure about availability of that kind of data at a national level. So no. So
yeah, as ever, it's models are always prisoners of the data that are available to build these models. Stuart, yes.
I just jump in there to say that it's in many respects it's not needed because the satellite is seeing what growing is happening.
Yeah.
So you don't need to worry about what's causing the variation. The satellite actually sees a variation and so on. So.
And it's looking at the same locations through time. Am I understanding that correct, Stuart? In terms of, and there shouldn't be any underlying change in the soils changes in the soil's fertility through time.
But if you've got a field that's got low fertility and a field that's got high fertility, the satellite will see that one field is growing more poorly than the other. So that's the difference.
Yeah. And Mary Roach has a kind of a question that relates to that, I guess, in some senses. Have you taken account the difference between old pasture versus new reseeded pastures in terms of growing grass in your machine learning algorithms? Again, it's a similar type of...
Yeah, for now, I have just considered whole farm. So these are, I think it works as few paddocks are reseeded in a farm and few are like old pastures. So for now, I've considered whole farm cover rather than going into each and every paddock because it's a national model. Yeah. So when we work at a lower few farms, like 1 or 2 farms, we can look at paddock variations. But for a national level, I think I haven't taken it into account. Yes.
Yeah, I mean, I think that there are questions flooding in, and I think these reflect the fact that the really exciting kind of research. Anne O'Malley is asking, is saying she's delighted with the use of artificial intelligence in measuring grass growth, and asks about whether you've done any work on looking at commonages and the impact of agri-environmental schemes in the last 50 years. And I guess that's likely to be future work for somebody else or in this space in terms of another application of this technology set. So
we have looked at commonages. One of the projects I mentioned there, TALAM, was designed explicitly to look at commonages. The commonages are difficult to look at for remote sensing because Risha's work is looking at fields, and that's your management unit, whereas the commonage, of course, is the entire thing. So we looked at ways of breaking down the commonage into different areas. So now we have that method worked out, and it's the basis of a new land cover product that's coming from the Ordnance Survey this spring.
Okay.
So therefore, from now on, we will have continual monitoring every 3 years of changes in commonages, and in fact, the whole country. For land.
Great. It's just another example of how our Teagasc research is changing how we understand the world around us. The final question for the moment for Risha is kind of getting a bit technical, I guess. Carol Quish, who I think works on an EIP on the Mulcair River catchment, is asking about the difference between the R squared and the 2 models in the January to June and July to December models, and what explains that that difference in terms of the model's performance. And I think I might know the answer, but I'll leave it to you to answer it correctly, Risha, since it's your research.
Yeah, so from January till June, we have better weather, and hence we have more number of images as well during the first half. So more R-square values. And during the second half, if you notice number of image points, they are lower as compared to the first one. Also, I have done till only October, October 2020, since we just finished the year. So I'll be updating it for December. So yeah, because of good and bad weather conditions.
So it's a function again of the number of observations in some sense that you have coming in to use in terms of estimating those models.
Yeah, I'm sure when I'll have more images for November and December, it might change.
Yeah. Thank you. A few questions for Rob. I'm just scrolling up to Gert Conradi asks, are estimated Ploss results available as published map layers at local, regional and national scales? Do you want to answer that one quickly, Rob, if you can.
Sorry, Kevin, could you say that again, please?
Yeah, it's from Gert Conradi. Are estimated Ploss results available as published map layers at sort of different spatial scales?
I haven't published any as map layers in relation to that project. There may well be some that are coming from Johnstown Castle.
Okay.
Just off the top of my head, I don't know the answer. Maybe Stuart knows.
No, generally speaking, no, because they're done on a farm by farm basis.
Okay.
It is one of the reasons we're trying to lobby for a national LiDAR coverage for lots and lots of different reasons, and the ability to do that, to do PLOS for every farm, is one of the cases that we're promoting.
Hopefully, there's someone from the department listening into the seminar who can take that pattern up. There's a number of questions from Marco Cosi and one's for you, Rob. Has there been catchment level mapping of water flows to look at how engineering methods might mitigate floods and manage floods and the outcomes that follow from those floods?
Yeah, well, I suppose the flood maps that we have been creating could be used for defining areas that could be flooded at particular times during the year. When we look at some of the catchments, particularly around Shannon Bridge, between Shannon Bridge and Athlone, there are large areas of land there that are submerged for maybe half the year sometimes. So these could be taken into account, yeah, for planned flooding, I guess, to alleviate stresses further down the catchment at different times.
Okay.
We can look at that nationally now, though. So, maybe we can start to look at it in terms of different parts of fields within farms as well that might perform a function in taking over water and having that then as a different land use, of course.
Yeah, and having evidence with which to remunerate farmers or compensate farmers for performing that function, indeed. Mark also has a question for you, Stuart, I think. And just to read it out, how close are we in terms of data mapping to having all we need to develop a national soil strategy and land use plan? It's like the billion-dollar man kind of question for you.
Well, we have the data to do the strategy. So we have the Irish Soils Information System that was created by Teagasc, so that's digital soil map. And we have this new national land cover map that's going to be published from the OSI in the spring. So we certainly have the data to do this strategy and to do the national policy impact, and so the environmental impact assessment on the strategy. What we don't have is the ability to test or apply the strategy at individual locations, principally because the soil maps as published are not designed to be used at local level. So there's a lot of work going on at the moment, like Rob's work on drainage and a few colleagues in Johnstown Castle looking at geophysics to try and get to move away from traditional sort of soil maps to say this is a certain soil series, and instead just get the physical properties or the nutritional properties of the soil at different locations. Once we have that, we can move from strategy to implementation at local level.
Okay. And a comment stroke question from our colleague Carl Richards in Johnstown Castle, who compliments the three of you on your impressive research and everybody else who's involved who isn't with us today in this space. And I guess this is sort of reflects some of the photometry or photogram, get the term right, but the use of smartphone cameras in people's hands out there. And that kind of came out of Rob's presentation. What are the plans to leverage citizen science to improve habitat mapping in Ireland? And are there kind of formalized structures, Rob, I guess, that farmers and citizens out there can use to basically contribute to the data sets that might be of use?
There are some organizations, I mean, Biodiversity Ireland, I think at the moment, runs campaigns where you can submit your own images of species and habitats as you come across them. The kind of research we're doing now with the deep learning really feeds into that, that anybody can submit an image. Doesn't need to be labeled, but it will be geotagged as it comes in from a smartphone. And we can feed that into the pipeline, you know, hopefully as a fully autonomous pipeline from the person taking the photograph. It gets labeled, it will train the EO data that's coming in into our archives, and that can then, you know, produce a product seamlessly, I would hope. But yeah, I think, you know, there's, as we develop the technology, you know, bringing the public into the equation is something that would be welcome, I think.
Yeah, we're almost out of time. In fact, we're just on the cusp of being out of time. So I'm just going to ask, just let Stuart, as someone who's kind of leading this and has been in this space in Teagasc for quite a long time. I hope you don't mind me saying that. Can I ask you the tomorrow's world question? You know, we all grew up looking at, you know, where are we going to go to with these technologies in the future? And feel free to talk about the agriculture land use space or other issues that you see these technologies being useful in using.
The big thing I think is the technology is going to be taken out of the hands of researchers. I think is all this information is now freely available. Everything you've seen today is all open source data you can get online. It's already been used by a lot of companies, individual farmers, I think will start taking it up. So I think it gets more and more democratized. The day of people like me sort of deciding what can be shown and what can't be is gone. In terms of technology, there's satellites being launched every day. So instead of having to, again, when I started this 25 years ago, you were lucky to get one image for a given field a year. In 5 years' time, you'll be unable to handle the amount of data you're getting in terms of observations for those fields. So I think sort of democratizing of data and then the abundance of data, those will be the two big drivers, rather than the actual technology of the sensors, because that's an incremental thing that happens.
So the next breakthrough will be how to choose what data to actually use and what data to not use in some sense for a given question or a given application.
Yeah.
Well, listen, there are a number of questions that we haven't had a chance to get to, but they have been recorded and they will be answered. And you can find a recording of this session on the Teagasc website. So you can listen back and watch the seminar again, or speed through to a little bit that you're particularly interested in. This has been one of a series on land use, and I think the last seminar of the series is coming up on the 20th of January. You can see that on the screen in front of you. And this, again, a change of gears from what we've been listening today in terms of Stuart and his colleagues' work. We're going to be talking to some economists and social scientists about how we as a society and how farmers balance our land use choices across traditionally productivist or economic driven drivers and new and emergent priorities, particularly relating to the environment. So I'd encourage everybody to tune into that seminar on the 20th of January. And with that, I'd wish you a Happy New Year again, and I hope you have a lovely day wherever you are. Thank you. Bye-bye.